Okay, here we go with the last video in the concepts section of Chapter 5 Forces. So this step is very important in problems with two or more objects that are part of a system to be analyzed. Usually mostly just two objects. Once in a while maybe more than two, but mostly two. So in its simplest form, you define a direction in just one axis, I guess you could say. So if we have, for example, ground and a block here, and a block here, then we might define right as positive, the positive direction, left as the negative direction. And then again, we might even, especially if friction is involved, define, it's up to you. If you want to stick with the convention of the x and y axis, then up's positive and down is negative. But I like to switch these sometimes. But what happens if we have, say, a table and a mass, like kind of a gross table. Anyway, and we have pulley, because all tables have pulleys. And we have a hanging mass. Then what we want to do is define a direction of motion along, say, the entire rope. So what you do is you draw an arrow and curve it with the rope. Because really what you can do, in one sense, is think of the rope as just traveling in one dimension. This rope here is traveling in the x direction only. It's in the x-axis, so that's one dimension. Even though part of this rope is traveling in the x direction and part is traveling in the y direction, you can consider the rope, in terms of tension anyway, to be all one direction. So what you do is you say this direction's positive and this direction's negative, or vice versa, depending on your preference. This could be negative, this could be positive. And also, again, with a ramp situation, it might even seem more like confusing to think of it that way. Looks like this block wants to have an arm. Whoa. Anyway, so what you can do is, again, think of the direction of motion of the rope as how you're going to define positive and negative. That's gross. Positive and negative. Again, I could have switched these. And so, literally, this system is going to move along this path. If this block is heavier, then it's going to go down, and it's going to pull this block up with it. But the rope is going to move along, like up the ramp, and then down the other side. Or if this one's heavier, it's going to go up this side and down the ramp. Right? So it's very useful to define this defined direction in this manner. This is yet one more example where you just have a hanging pulley, block on this side, and a block on this side. What you could do is define, like maybe plus here, minus here, define a direction of motion, again following the rope. And I'll do an example or two where I utilize this technique. That's all I wanted to say about that. And finally, the geometry of net forces on a ramp. So let's draw a nice big ramp. That's too steep. Nice big ramp. Alright. And on this ramp we have a block. First, oh, and also the angle of the ramp is theta. First off, let's pretend this is a free body diagram, but as you already know by now, if this is a free body diagram, you're not supposed to draw the ramp. You're just supposed to draw the object. So the ramp is illegal. But anyway, I can label some forces. So let's label gravity first. So gravity goes down like that. Then let's label the normal force. And remember, the normal force is perpendicular to the surface. The surface is the ramp, and so perpendicular to the ramp is up like that. And there may be friction on the ramp, and so if the block wants to fall down this way, friction is going to try to oppose that motion. So friction is going to act up the ramp, at the angle of the ramp. And you can imagine if I had a pulley here and a rope coming up and around, there would be a tension here as well. First thing you should notice is these vectors are not all perpendicular or parallel to each other. And that should set off some warning bells in your brain saying, components, components. So how you want to set up the geometry of a ramp is instead of making your XY axis like this, where this is like plus X, this is negative X, and this is Y, the Y axis. That might look good for gravity. That puts gravity in the Y-axis, but you got friction going up like that, and so you'd have to break friction up into components, and you got normal going like that, and you have to break up normal into components. This is not the ideal way. Well, it's still a possible way. It's not the ideal way to handle ramp problems. So let's do it differently. Let's tilt our XY axis so that it's in the ramp's frame of reference. By that I really just mean that the x-axis is now parallel to the surface of the ramp. The y-axis is perpendicular to the surface of the ramp. What that does is it puts the normal force in the y that's gross. In the y-axis. It puts friction or maybe tension in the x-axis, and now only gravity is needs to be broken up into components. It's actually really convenient to do it this way because when the y component of gravity, sorry, I should put the g here. The y component of gravity, Fgy, is literally responsible for making the normal force. Why is that? Because if we've discussed this earlier, the block isn't moving into the ramp because the ramp's like nice and solid. The block isn't shooting up off the ramp that way, so the net force in the y direction must be 0. F net y equals 0. If that's the case, Fgy has to equal Fn. This normal force has to be cancelled out by the y component. It's an arrowhead. The y component of gravity. That's beautiful. And then finally, you got the x component of gravity here, and that's the force responsible for pulling the block directly down the ramp. And so often you draw Fgx here. And you can see they all come from the center. Oh, this brings up a good point. I didn't actually mention this back here. Step 5. Please add this. Never, good thing I remembered, never draw force components. Suddenly I'm writing in cursive. What's going on here? Force components on on a free body diagram. So what that means is you wouldn't, if this is a free body diagram, you wouldn't draw Fgx and Fgy, just Fg. You can draw a separate diagram that is not your force body diagram that has these, which you usually will want to do, but on the AP exam, if it says draw a free body diagram, don't you dare label these components, just FG, and that's it. Alright, well, how do FGX and FGY relate to FG? In other words, what angle, this angle, there must be an angle here somewhere that relates to the angle of the ramp. What is that relationship? It's not necessarily, unless you're like a super geometry brain person, which I'm not, it's not necessarily immediately evident which is which. So how do I, you either memorize it or you figure it out each time. I never memorize it because I don't memorize anything. So how do I figure it out each time? Well, I like to draw a line here. I like to extend this out. And I like to draw lines straight up. And then I'll just make a triangle like that. So as you can see, this line to me represents FG. This line represents FGX, and this represents FGY. And now, because I've drawn this down here at the tip of the ramp, right next to this angle here, it's easy to see that it's easy to progress through. This is a 90-degree angle, so this little angle here must be 90 minus theta. And then doing the same reasoning as we just did, this is a 90-degree angle, and if this is 90 minus theta, this must be theta. And so, as you can see, FGX is opposite the angle. That's going to be sine FG sine theta, and FGY is adjacent to the angle. It's going to be FG cosine theta. And so that's really the geometry of the net forces on the ramp. And these are going to go into your net force equation, as you'll see in some examples. But I really just wanted to show you how to do this geometry so that you can either now memorize this, which might be useful if you like to memorize things, or just remember the little trick that I just showed you to figure out the geometry of it. Start at the tip of the ramp where the angle is here and work your way around. That would have worked also if you did this triangle. If this is a right triangle, if this is 90 minus theta, then this becomes theta up here, right? And here's your right angle. So same idea. Alright, so that concludes the concepts of Chapter 8. I'll have a few other sample book problems for you to look at that demonstrate a lot of these. It actually should demonstrate all of these. And that'll be good for Chapter 5. Good luck.